Hello, my friendly flat earthers. You always complain that we globe earthers don't do any real experiments, and you suggest that we somehow find another earth and try to pour some water on it to see if the water will stick. And since we are unable to do that, you claim that you are right. You also claim that all the images that we show you from just about any experiment or any observatory that we have ever used throughout the times are faked, mainly because the blue marble image, which is an artistic impression on how the Earth looks, is claimed to be evidence that NASA is somehow cheating us. So I was thinking, well, I'm going to give you some real CGI. Now, this is actually a relatively serious experiment that I'm going to take with you, because I have gotten into the game Star Citizen. And yes, it's a game, I don't deny that. And you could claim, well, that's not really real, that's not real, and this is only game, this is only... Yeah, that's true. I could also have chosen a more advanced system like Orbiter or something like that. But I think that for this experiment, this game will suffice because it holds a lot of the physics that we need, and also the controls are relatively simple. You also have VTOL in Orbiter, but it's much more complicated because you have all the flight mechanics and all the flight physics in there. We don't really have that here. All the ships are hovercrafts. But nevertheless, the idea here is that I want to show you that when you're standing on the surface of a sphere, a really big sphere, your horizon will look flat. It just will. So let's get started. There are some things that we need to consider here, some caveats, you could call it. First of all, the field of view here is somewhere around 86 degrees. So it's a relatively big field of view that would be equivalent to a somewhat reasonable sized wide angle lens that you also complain about. The other thing is that the planet here is only in game size 3 kilometers in radius, so it's twice as small, if you will, as the real sized Earth. And when you combine those two informations together, you'll see that we actually we would expect to see the curvature much sooner here than we would on Earth, because Earth is double the size. But nevertheless, let's start with one experiment and let's see what we can see here. Here's my ship. Yes. We can see some plants. Yes, this is an alien planet in a game. Yes. But this is what you would expect to see if you were standing on a sphere. Right, and I'm going to show you that this is a sphere in just a minute. But let's take a look. We can see, let's start with the first experiment and sort of get an impression on what we can see here. This is our field of view, right? This is what we can see. Let's take a peek on those two mountains out there. Let's try to zoom in on them. This is what we can see. All right, try to keep that in mind. Then we're going to go up on this hill here, this little hill we have here. And then we're going to test the exact same thing. Now, according to the spherical model, we should be able to see more of those hills because we have gained altitude. On a flat Earth, you shouldn't be able to see more. Well, technically you should. If there are obstacles in the way, we also had obstacles here. But in general, you should be able to see the same amount whether you're standing on the ground or you're standing on a hill, because it is flat. It's a flat plane. Alright, so let's take a look. I think the mountains were out here somewhere. Two of them together. I think it was over here. There they are. I will argue that we can see more of them now. Let's take a look again. Yes. I would definitely argue. Let's go down again. I'll try to keep sort of a 90-degree angle to the mountains out there so that we have a pretty good idea of where they are. But I will argue that they are... we can see more of them. Now, so while I'm going down here, let me say why I think this experiment is valid. Let's discuss what it is we want to show. We want to show how things look if you're standing on a sphere. Now, whether I go out on the real Earth, yes, you can see more of the mountains. I will agree that there's something in the way, but this hill here, that obscured less of it before. Alright, so why is this experiment valid? This experiment is valid because what we want to test is how things will look if we stand on the surface of a really big sphere and try to look out and see the curvature. Now, I hope that you can agree here. There is no discernible curvature. Yes, there are hills, there are tops, there are rocks and all those things, but in general, the horizon is completely flat. So from a flat Earth argument, this world here should be a flat plane. And even if there were a ship flying past us here and going down below the horizon, you would still argue that, or a car, but there are not many cars out here where I'm now. You would still argue that this should be a flat plane and it would be something with perspective and all that. That is the explanation as to why we cannot see that car or that ship or whatever it is anymore. But let's get the first thing, the first observation that we do here. We cannot see any discernible curvature. I hope that we can agree on that, and I can sort of look all the way around. I'm sorry it's a little jagged because I'm using my mouse for it. There's the star. But nevertheless, let's go up on the hill and get a better view. So we're going back up again. And yes, if you want to know, I'm dragging time a little bit because I really want to sort of get the big finale when we go up in the ship here using vertical takeoff to see when we can see a discernible curvature. And again, keep in mind this sphere here, although it is big compared to a human, a radius of 3,000 kilometers, that is pretty much. Let me see, is this the tallest peak? No, it's not. I think it's over here somewhere. Not that it makes a big difference, but I want to see all the way around, and I might think it'd be better to go up here. Alright, so out here we have a little landing pad and something like that. But, yes, as you can see, I would argue that this horizon here seems really, 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 really flat. So, this is a flat world, right? It's flat. And there's some NASA CGI. Alright, so yes, it looks flat. I hope we can agree on that. So the premise for this experiment here is that we can all agree on whether I'm standing on a hill in a virtual world, which has been modeled in all the way you can think about as a sphere in space. I am given, compared to this world here, the same size as a normal human being, and this world here is roughly half the size of Earth, so roughly 3,000 kilometers in radius. If we can agree on that fact, that this represents what we would expect to see in real life, then we must accept this as a valid experiment. Otherwise, there are some graphical glitches here. Otherwise, we would be at fault with our postulations, because we cannot on one side claim that on Earth, which we claim to be a sphere, has to hold some certain observational facts, something that we can see, something that we claim is distinctive for standing on the top of a sphere contra standing on the top of a flat plane, and then argue that those same considerations doesn't work for a modeled sphere or a model flat plane in a virtual world. And this is a virtual world. That is why we use it, because we can actually model something as big as the Earth, or just about, and show how the physics behave, how the visual cues behave. So now we are going to take this ship up in the atmosphere. I think we're going to go for the first part something like 100 meters at time or something like that. And then we're going to see when we can actually see a discernible curvature, how far we have to go up in the atmosphere before we can see that. Alright, we are now at the surface of this planet, and I will agree that those who have made this planet, I'm not sure where they have set the offset of the altimeter, but as far as this is concerned, we are 840 meters above some level. So that means the first 100 meters we go up, we need to go to 940 meters. So I'm going to try to do that. So now we are at 940 meters. That is 100 meters up, and I still can't see a discernible curvature. Let's go further up to 1040 meters. Yep, too much. Let's go down a little bit. There we go. No, it still looks round. Sorry, it still looks relatively flat. Let's go up to 1140 meters. Still looks relatively flat to me. There might be some areas around where you can see a little bit of curvature because of the hills and all those things, but generally I would argue that it looks pretty flat still. And please keep in mind that we are having a pretty wide field of view. If we narrowed that field of view in, it would be more comparable to what we're used to seeing. So let's try to go up to 1200 meters. No, 1300 meters. Still the same as far as I see it. Let's go to 1500. Might be some, but still, if you look in between the HUD display up there, it still looks pretty flat. Not that round to me. Let's go further up. Let's go 2000 meters. Yeah, now we might be able to see a little bit, but I really don't think so, and there's a lot of atmosphere right now. Let's go further up. Let's go to 3000 meters. Now there might be a little bit discernible curvature. It's very little, but it is there. And again, remember, this sphere is roughly the size of the moon, something like that. Our moon in the solar system, 3000 kilometers. So it's not as big as Earth, it is half the size of Earth. Let's go to 4000 meters. Still looks, well, there's a little bit of curvature, but generally I would say it still looks, if you look sort of from edge to edge, you can see a little bit of curvature, but not much. Let's go to 5000 meters. So now we are 5 kilometers out. You might argue that you can see a little bit of curvature. I'm not sure I would argue that, but well, that's up to you. If you look at along the edges, yes, but it might as well be hills or mountains or something like that. So I'm trying to get to keep the ship steady with my mouse here. It's not going that well. So if we rotate a little bit around, you can see if we do it like this, it looks pretty flat to me. If we go over here, it looks pretty flat. So only if we're in this sort of direction here, it looks round. It does have a little bit of curvature. And I would say, well, again, the premises for this experiment is that we recognize that this planet is half the size of Earth, and we have almost 90 degrees field of view in the game here. So we have a relatively wide field of view. Let's go further up to 6,000. A little bit above, but now I can definitely see some kind of curvature. It's hard to see because of the atmosphere, but it's definitely there. Let's go up to 7. No, let's go to 8 right now. Now we are 8,000 meters. Well, actually it's 7,000 and something, 7,200, because we started at 810. Now I would argue that in order to see discernible curvature, you need to be pretty high up in the atmosphere in order to see it. Now this is a relatively small world, and we have a wide field of view again, so... But at this altitude here, I can definitely see some kind of curvature. If you follow the atmosphere, there's not much, and I would argue that it is more precise to follow the atmosphere around than the actual ground itself. And the atmosphere still looks pretty flat to me, pretty linear. There's a little bit of curvature perhaps, but not much. And it's also hard to see because some of the atmosphere is getting obscured by the fact that this star here is setting. If you follow the ground, you can be a little bit disoriented by the fact that there are hills and mountains and all that. Let's go to 10 kilometers. Alright, so now we are 10 kilometers up in this atmosphere. 10,050 actually. So if we want to be 10 kilometers up, we should go to, let's just do that. Let's go to 10,810. Something like that. And I think I'm going to just move us a little closer to the star here so that we see it setting. So that we don't, I might change the altitude a little bit, but so that we have more light to work with. I'm trying to keep the altitude as much as I can, but I can't promise anything. See you in a little bit. Alright, so now we are back, 10,810 almost meters up in the atmosphere, 10 kilometers. And depending on how you look at it, if you look at the atmosphere, well, there is some curvature to be seen, but not much. And if you do it like this, I would argue it still looks pretty flat. So let's go to 15 kilometers. No, let's go to 20 kilometers. No, let's just go to 15. So now we are roughly at 15 kilometers in this atmosphere. And let's try to move the ship a little bit around. Let's see if we go down like this. You can see that now there definitely is some discernible curvature, even if you look at the atmosphere. If you turn the ship like this, well, it again becomes pretty flat. So by narrowing in our field of view, and still it's not that kind of narrow field of view, but by doing like this, I would argue that like this, I can see the curvature a little bit. Doing it like this, it still looked decent flat. So let's go to 20 kilometers. And let's just keep it at whole numbers now, roughly, because those 810 meters doesn't really matter right now. So let's just go to 2100. There we go. Let's take a look again. Tilted. It still looked reasonable flat. If I do it like this, I can definitely see that curvature, but then we also have this really wide field of view. If I do it like this, it still looks pretty much like a line. Let's see how far we need to go. Let's go to 30 kilometers. $30K. And having a little bit of trouble with blood to the brain. Now I can definitely again see the curvature. Tilt it like this. Not really much. Alright, so what do we need to do in order to convince ourselves that this actually is a sphere? Let's try to get as far away from this planet as we can right now. And for this we need to enable the main boosters here. So let's go all the way out until we cannot see those numbers changing anymore. See, now you can definitely see the effect of the wide angle. As you can see, as I move it around like this, the curvature becomes more exaggerated. But still, if I look at it, it is a pretty big sphere, right? But now we can at least convince ourselves that it is actually a sphere we have here. Let's just try to quietly move away from this planet. And as you can see now, the numbers have disappeared because we cannot see anymore how far up we are. It cannot measure it over the surface. But even with this wide field of view, if we look at the planet itself, we cannot see it even now. It's too big for us to see. I think I'm going to speed up the video now so that you don't have to wait. So now we are actually so far away from this planet that we can actually observe it in all its glory. Now, as you can see on the top, there are some graphical glitches with where the atmosphere ends and all that, but generally this is how you expect to see a planet like this. And let's try to figure out how far away we actually are from it. You can usually do that by finding some. We are there. Let's see, set the route. What did it say? It said 900. That's almost. We're almost 1,000 kilometers up right now. And again, we have a relatively wide field of view. If we narrowed it in, we needed to go further. But I've said a couple of times on some of the Danish Facebook groups of flat earthers that in order to see the curvature of the earth, you need to be at a distance that is roughly comparable to its radius. And in this case, we are almost 1,000 kilometers out, and the radius of this planet here is about 3,000 kilometers. So that's at least comparable to the size of the planet. Now, let's go all the way back, because now you can definitely see, I hope, that this is a sphere. And let's set course for the ocean here and take a look out on it. And you can roughly see, let me see if we can find any landmarks. We probably cannot do that. No, not at the moment. But let's set course for this. Again, I will speed up time and then I will see you there. So now we are far enough into the atmosphere that we can actually measure it, and you can also see that the angle insertion device or the ascent device actually recalibrated for the gravity on this planet here. And when we land here, I guess we can actually see one final thing that I think is also pretty important, and that is we can see how we can re-see, whatever you want to call it, the sunset, just like we would expect to see it on the Earth if we were at the surface and then climbed up just a tad. And see if I can find somewhere we can do that. But we need to go into the brighter part of the atmosphere.
Proximity alert. Deck. Landing gear deployed. Proximity alert. Starboard. Landing complete. Launch complete. Proximity alert. Head. Proximity alert. Deck. Landing complete. Engines offline.
Okay, so now we're sitting here and waiting for the sun to set. Now, one of the key arguments from globe earthers is that one of the consequences of living on a sphere, and now we can certainly see that this is a sphere that we are living on here in this virtual environment, is that if you sit down and you watch the sun go down, then as soon as the sun has just gone just below the surface, you should be able to stand up and see it set again. And then again, if we take the ship and go further up, we should be able to see the sun set once more. So let's test it out as the last part of this video. Isn't it lovely sitting here in this virtual environment and see the sun go down, nice and quiet? Almost there. And there. It is just below the surface. Let's try to stand up. Oh my, there it certainly is again. We can see the sun go down for the second time. How nice. And now it goes below the surface once more. So the final thing we can do is to take this little ship here and then just go, let's just try to go 50 meters up and see whether we should be able to, well, that certainly wasn't a good landing. See whether we should be able to see the sun again, That's one of the predictions of living on a sphere. So let's try it out. One of the other reasons that I prefer using Star Citizen, even though it's a game, compared with
Aegis combat assist activated. Systems green.
Orbiter, is that in Orbiter you cannot go outside the ship, so anything and everything you see is defined by the ship you're in. You can actually go out and wander around in this game here, but if you see past that the wing physics is not as advanced and that most of the aircraft that you have are hovercraft, so they can basically hover everywhere they are, I could fly this ship up and point the nose straight down and it would just stay there. Of course, if I turned the engines off, it would crash, but nevertheless. So now we are at an altitude of 728 meters. So in order to go 50 meters up, we need to go to 770 meters. So let's just take off slightly.
Launch complete.
Up. Need to adjust it a little bit. I'm not sure why I keep looking down, but it's a bit annoying. Alright, so let's turn the ship over to the sun.
Landing gear retracted.
Here should the sun be. And now we are at 1800 meters. Let's just quietly try to go up and see when we can see the sunset again. Now, on a sphere, the sun should be visible at some point. If this was a flat plane, and it isn't, the sun should be visible at all times, because it doesn't go below the surface. But let's try to go up nice and quiet. Alright, so it's pretty obvious that I waited a little bit longer than I should. And also the days on this planet here is definitely not the same as it is on Earth. There it is. Can you see it? Now the sun is becoming visible again. And this is one of the consequences of living on a sphere. You can actually get the sun back into your field of view by raising your altitude. So now that we have finished playing a little bit around with this game here, let's try something a little bit more serious. So one of the things that I really wanted to get a grip on or get a handle on was the lack of models, the lack of flat Earth models, and to show you that the flat Earth model as it is now, the way I've heard it described, is really completely impossible. That's what I wanted to show you. So my idea was that I wanted to make a working flat Earth model in 3ds Max, as you can see here on the screen right now. And what I did was that I made a cylinder and I flattened it, and then I got sort of a big disc, a big pizza in space, whatever you want to call it. And then I placed several cameras around. I placed a camera at the pole, as you can see here. Let me show you right here. This is the camera of the pole. Then I have a camera roughly placed where I live, Europe, something like that. Then I have a camera placed right at the equator. And then the final camera is somewhere further out. Also, let me show you here. I wanted to try to show you how it looks when you look at the things at different distances. So I placed a physical camera. As you can see, it's placed just about here. Let me see if I can zoom in on it. No, but it is somewhere here around on this big, you can see the disk here, that's the disk. And then I finally placed the sun. You can see the sun is here. And then I have it move it around. At this point, I just placed it at equator, but to sort of signify when we have equinox, but it can be placed just about anywhere on this model, so it is room for further improvement or testing or whatever you want to call it. So yes, that's it. Let me see, what else can I say? What I did was that I wanted to take pictures of these triangles. These triangles, that you can see here, pyramids, are placed at various distances along this. Let me just show you. Pyramid 1 is placed. They are placed relatively close by. You can see them here. So yes, let me show you. The physical camera is placed here. It doesn't look, it looks this way, but I think it's obscured by this camera here, which is, I think this is camera 1, yes. But the physical camera is here somewhere. But nevertheless, I've placed these, you can see them here. Pyramids, not sure what pyramid 1 is, but yeah, it's there. I'm not sure why it got on the attachment point, nevertheless. So we have pyramid 1, 2, 3, all the way out here at various distances. The furthest one being around 500 kilometers away. All right, so yes, I should mention that. This disk here, let me show you, it has a radius of 20,000 kilometers. Now, as far as I know it, you can set a specific unit in 3ds Max if you want to. I could have gone with meters, but generally you just use these units that 3ds Max has. So you could call it meters, centimeters, kilometers, parsecs, light years, whatever you want to do, as long as you are pretty consistent on what you're going to do around it. So that's the real thing here. Other than that, you can do whatever you want. So I've placed, you can see that the disk here is positioned at 0, 0, 0. So the pole is at the exact center of the disk, just like it should be. And then I've placed these, well, the furthest one is 500 kilometers out. So that's pretty far. According to any flat earther, that if something is more than, I don't know, 30 miles or something like that, it should be completely obscured so you cannot see it. This is also what we generally observe. So an object 500 kilometers out should be pretty much obscured so you cannot see it. This is going to be interesting to see whether that's the case. So let's take a look at that. All right, here we are with the first image. We are looking at the flat earth, at these pyramids, at just about 90 degrees angles. That's pretty wide, and you can see all these pyramids stacked up just along there. You can see every one of them. Now, let's try to zoom in a little bit. All right, so now we are at 45 degrees, and we can still see the pyramids. You can see them stacked up all along the way down there. So let's go in even further. So now we are looking at all of these pyramids at 20 degrees angle. Before it was 45 degrees angle. And I can still see them, all of them in their correct sizes. When are they going to be obscured? Let's try to go to 10 degrees. So here we are. We're looking at these pyramids at 10 degree angle. And I can still see all of them. This is pretty bizarre. Let's try to go to 2 degrees. And here we are, finally, at 2 degrees. And I can still see the last pyramid just as tall as it would look like anywhere else. So I really don't understand this. Well, maybe it's a problem with the model, right? Yeah, it's just, I think it's that. Let's try to look at those images, animations of the sun going around on the Earth. So now we're looking at the sun going around over the flat Earth at the North Pole. And I must admit, it doesn't look right. It is definitely not how I would expect the sun to look when it goes around above the North Pole. Well, let's try to go to around Europe or something like that. Yeah, here we are. No, that is definitely not how I see the sun here. No, not at all. Let's try to go to the equator. So this is the equator, and no. That is also not correct. That is also not how I expect to see things. This is so strange. This is not how the sun looks. And now we're below the equator. No, that's not. No. That's not accurate at all. What in the world is going on? This is strange. Now, of course, we cannot really have a flat Earth model without also trying to test it up against a spherical Earth model. So that is what I have done also. So you cannot really see it here. This is the Earth. This is a sphere. And out here somewhere, let me see if I can go all the way out and zoom out as much as I can. See if I can just center on the sun. Rename display property. No. But we're just going to move all the way out there to it. It's somewhere out here. Or not. Maybe we can see it down here. Let me see. Cameras. Let's just go with perspective and see if we can go all the way out so we can see the sun. It is here somewhere. What I did was that I made the sun, as you can see here, as a sphere with a radius of 695,510 kilometers. And I added as much segments as I could, and it's smooth and all that. And I placed it. Just show you. And yeah, the furthest it could come out. So it's 100 million kilometers. I think it cannot move it any further out. I actually tried with 149, but apparently it doesn't work that way. But it's pretty far away. So maybe I should reduce the size a little bit. Let me see if I can actually get it out there. Let me see. 149. No, it goes to 100, the max that it can. So yeah, but it's pretty far away. Then I also created an Earth. So here's the Earth. With 6,400 kilometers. So that's the sphere, that's the radius of this Earth here. And also here I have placed various cameras around. At first I wanted to do it the real way. Let me just show you first that I have again placed this time I called them pyramid cam. So this should be, let me see if I can find pyramid cam. It is there. That's the pyramid cam. And it is here. So it is looking in this direction here. Yeah, I can see the pyramids are not there any longer. Let me see if I can. I'm not sure where they went. But they are there. Did they go to the top? Is that it? Well, there they are. Yeah, they did. They moved to the top. All right. So that's a little glitch that happened after I took the images, fortunately. But the pyramid cam was here. And again, I placed pyramids at various distances throughout so that we could test it out. And furthermore, let me show you this, how it would look if we look at something on the Earth at various distances. And I also changed the camera angles just like before so that we get the correct images. Let me show you what happens. So as you can see here, if you look at these cameras here, as I change the time slider here, they move around. Now at first I tried to attach them to the Earth and make the Earth rotate, but for some reason 3ds Max just couldn't handle that, so whenever I tried to animate that timeline down there, it just showed me the sun at a certain point, nothing more. So the other idea that I got was to, instead of make the Earth rotate, would be the most realistic. I would instead just put the cameras on little circles and then place them above the Earth. So technically that is not completely accurate because it is not what we see, but in general it is the important thing here is really not whether the Earth is moving or not. The only thing we are looking at here is the sun in order to see how it looks when the sun is setting. As you can see here, the cameras move around along the Earth. You can also see it down here. When I change the timeline, the cameras move around all the way, all of them, along the equator. So let's go in and see how these animations looked. Alright, so first we're looking at these 90 degrees and we can see the pyramids going out in the distance, but they look different. They look smaller, just like I would expect them to look. Let's try to zoom in. Alright, so here we are at 45 degrees. And yes, I can see the buildings getting closer and closer and closer, but they are still getting smaller in the distance. This is interesting, because this is what I would really expect to see out there in the world. So here we are at 20 degrees, and I can see we are getting closer to the pyramids. We're zooming in, but still, the furthest ones away seem to be going over the horizon, then over some bulge, and then disappear. This is what I see when I look in the world. Let's zoom further in. Alright, so here we are at 10 degrees. And I can see that we have gotten closer to some of the pyramids, but the first three of them still seem to get smaller. This is very interesting. So now we are at the final zoom. We are looking at 2 degrees angle, and I cannot see all of the pyramids. You can see that on the textures. Some of them have simply disappeared bottom up. This is what we would see on the world. This seems to indicate to me that our world is not flat, but spherical. But let's not get our hopes up yet, because we still need to compare how it looks when we look at the sun. Let's do that. Alright, so this is the way the sun would move according to my 3ds Max model. When we are sort of standing at a point, not exactly at the North Pole, but thereabout, and watching the sun set and go up at equinox. And this is pretty much what I would expect to see. Let's try at Europe. So this is how the sun should rise and set when we are roughly where I live. And besides the angle, I can certainly confirm that this is generally how I see the sun rise and set from where I live. So this seems to be okay. Let's try the equator. Alright, so at the equator I would expect the sun to rise almost straight up and go straight down, sort of a 90-degree angle, perpendicular to the ground. And from what I see of my model, if you take the weird camera angle, because that's the way 3ds Max handles the camera, it seems to be pretty accurate. This is what I would expect to see. So now we are below equator. And again, if we take that weird camera angle, that the ground seems to be slanted, this is also what I would expect to see. This is the way I would expect to see the sun go above the sky. So, well, it seems that flat Earth model, it certainly has its problems. In conclusion, I really hate to break it to you flat earthers, but as you can see here, the model that you are proposing, the way you say the world should work, the way the sun should move, the moon should move and all that, it is not only inconsistent with what we observe in real life when we go out and look, it is just generally completely inconsistent with what we can make of simple models. This is just a simple 3ds Max model. There's no physics or anything of the sort bound to it. It is simply me making a flat plane, a flat round plane, placing cameras at various points that look at a sun, and then try to see how that sun would look when we look at it. And please dispense with all that perspective talk and all that, because these are cameras that are set just like optics would work with different focal length. In this case, it was 50 millimeters, or something like that. So they will behave just like normal cameras would behave. So if we were to expect to see perspective with our own eyes or with a camera in 3ds Max would also record that. So no, there's no perspective at work here. It is simply just the flat Earth model that is completely and utterly inconsistent with what we observe in the real world. Thank you for watching, and I don't expect you flat Earthers to like my video, not at all. Probably you'll dislike it instead. But nevertheless, if you like the video, give it a thumbs up, and if you want to see what I'm up to next, then hit that subscribe button and the bell next to it. And then you will see what I will do next. Bye bye.